Thank you, Ricardo. Thank you, everyone. It's a great honor for me to present our recent journal paper under submission, which is named by Temporal Action Localization with Variance-Aware Networks. I'm Tingting, and my work is done with Dr. Christos and also my supervisor, Professor Yanis Patros. I stood the task of temporal action localization. It's to detect actions in a video, and you have to find the start and end of the action in that video, in that untrimmed video. So if we want to formulate it, the input is a video, the output is a set of video clips, including the action category, and also the start and end of this action. So for the classical approach of CAN-based methods, people usually make classification of a subset of candidate video clips and then do regression to refine the boundaries. So the bottom is the pipeline. Given some video clips, we feed it through the feature extractor and then detector to make classification and regression. However, as the video clips are with arbitrary lengths, what should we do to feed it to a fixed size input detector? The key answer is pooling. So as to pooling, let's say we have such a video clip which have n units. Well, for each unit, it consists of 16 frames, and each unit is represented by a vector of size d. So this embedding matrix is the feature of this video clip. And what we would like to do is to compress this with a feature to a smaller one with size k by d. And well, n is much more bigger than k. What should we do? So we just divided n units into k part. So for each part, it has n divided by k units, where we take the mean to be the final feature. So it's the pooling operation. However, applying this pooling operation will lose some information. So in this paper, what we do is we not only get the mean, but also the variances to be the final feature. So our final feature is multiple Gaussians instead of just the mean. For the baseline network, we have for the video clips, it has been converted to a fixed size feature, and then it goes through the detector to do classification and regression. In our paper, we mainly focus on the regression task. So, but now, so if we want to simplify that, it's the function. It's the most simplest way to show that. However, now we not only have the mean, we also have the variances. What should we do? The simplest way is to concatenate both the mean and variances together to be the input of the network, and then we train as the same way as the baseline network. However, in this way, it will double the number of the input parameters. So in this paper, we propose a more efficient way to use the variances. So we model the input as Gaussians, and the input can be propagated from the detector function f to the output also as a Gaussian distribution. So as we can see that the mean of the output can be, the mu of the predictions can be considered as the regression boundary. But how about the standard deviation? It could be considered as the uncertainty of this prediction that our model has made. So now we need to know how to learn it. For the baseline network and the concatenation methods, we use the standard L1 loss like this. However, for the propagation methods 1P, the output is a Gaussian distribution. Well, we model the ground truth also as a Gaussian distribution. So to measure the distance between these two Gaussian distributions is to use the KL divergence here. So in this paper, we take KL loss as the loss function. As to the intuition behind this KL loss can be shown in this example. Let's take T as our ground truth. Well, P1 and P2 are two predictions of the network. If we use the standard L1 loss, then the loss from T to P1 and P2 are the same. However, they have different variance here. So as we can say that our network is more uncertain toward the prediction P2 than P1. So if we take KL loss, then the loss between T and P2 are smaller than the one between T and P1. So in this case, by assigning larger variances to the noisy tuning samples, our KL loss can downweight the noisy samples to enhance the robustness of the network and improve the performance. This is the realizations of the uncertainty stuff. For the first row, it can be seen as a video sequence. Well, the green bars are our ground truth, and the red bars are the predictions of our network, and the bell curve under the red bars are the Gaussian distributions that our network has been predicted. So it's worth noting that when the proposals are close to the ground truth, and our predicted variances are relatively low, well, for the ones like this, they are a bit far from the ground truth. So our variances tend to be larger. To say I'm not certain with the boundary, so it indicates that our network is attempting to cover the whole action. It's consistent with what we are talking before about the uncertainty. So now we had then show the experiment on the famous data set Sumos 14. Well, as we can see from this red line, from this green lines, is the result of the concatenation methods. It in general improves the result from the baseline, especially when TLU is larger than 0.5. Well, the right line shows the result of the propagation method. In general, it outperforms the result both of the baseline and also the concatenation methods. Well, in table 2, it shows the number of the parameters. So this number of parameters are related to the reference time and the calculation flops. So we can say that the concatenation almost double the number of the parameters of the baseline, while our propagation methods are the same number of the parameters with the baseline. So we can say that our propagation methods can improve the baseline without taking any extra parameters. It shows the effectiveness of our network. So that's what I have for my presentation. And if you are interested, please look into our paper, which is here, and our code will be released soon. Thank you for your attention. Thank you.